Tonight, we're going to explore one of the most fundamental aspects of reality: gravity. You experience it every single moment of your life. It keeps your feet on the ground. It keeps the atmosphere around Earth. It keeps Earth orbiting the Sun. It governs the motion of galaxies billions of light years away. And here's the twist that's going to change how you see the universe. Gravity isn't actually a force at all. It's something far stranger and more beautiful than that. And here's what's going to blow your mind. Everything you think you know about falling, about weight, about objects being pulled toward Earth is wrong. By the end of tonight, you're going to see reality in a completely different way. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Consider what you think you know about gravity. You drop an object and it falls down. Simple, right? You've been told since childhood that Earth's gravity pulls things toward the ground, that gravity is a force pulling you downward, that the sun's gravity pulls Earth into orbit around it. Most people believe exactly that. Schools teach exactly that. And while it's not exactly wrong, it's incomplete. It's like saying the Earth is flat because it looks flat when you're standing on it. It works for everyday purposes, but it misses the deeper truth. The story of how we came to understand gravity is actually one of the great intellectual adventures in human history. It's a story that spans centuries, involves some of the greatest minds who ever lived, and fundamentally changed how we see reality itself. Isaac Newton figured out the mathematics of gravity in 1687 when he published his book Mathematical Principles of Natural Philosophy, usually just called the Principia, one of the most important scientific works ever written. The impact of this book on human civilization cannot be overstated. Before Newton, ideas about why things fell or why planets moved were mostly philosophical guesses mixed with religious dogma. Aristotle thought heavy objects fell faster than light ones because they had more gravitas, an inherent property of heavy things seeking their natural place. He believed that objects made of earth and water naturally sought the center of the universe, which he assumed was the center of Earth. Fire and air, being light elements, naturally rose upward toward the celestial spheres. This made intuitive sense. Drop a rock and it falls quickly. Drop a feather and it drifts down slowly. Obviously, heavier things fall faster, except they don't. But we'll get to that. Medieval scholars spent centuries debating why objects fell. Some thought objects fell because of horror vacui. Nature abhors a vacuum, and objects rush downward to fill empty space beneath them. Others proposed that objects fell because of impetus, an internal force within falling objects that drove them downward. Some suggested that angels pushed things down. These weren't scientific theories in the modern sense. They were philosophical arguments based on logic, theology, and limited observation. Nobody had a mathematical framework that could make precise predictions. Nobody could calculate exactly how fast an object would fall from a given height. Nobody could predict where the planets would be a year from now with any accuracy. Astronomy was mostly about recording where planets had been, not predicting where they would go. Newton changed everything with one insight. The same force that makes an apple fall from a tree also keeps the moon orbiting Earth, and Earth orbiting the sun. This was revolutionary because it unified terrestrial and celestial mechanics. Before Newton, people thought the heavens and Earth operated under completely different rules. The celestial realm was supposed to be perfect, unchanging, eternal, following divine principles that were fundamentally different from the corrupt, imperfect, temporary terrestrial realm. Aristotle had taught that celestial objects moved in perfect circles, because circles were perfect shapes befitting the divine heavens. Circular motion in the sky was natural and eternal. Linear motion on Earth was temporary and imperfect. The idea that the same laws governed both realms was philosophically radical. It suggested that the universe was unified, governed by comprehensible mathematical principles that applied everywhere, not just on Earth, but throughout the cosmos. It suggested that heaven wasn't fundamentally different from Earth, that the moon and planets were physical objects following physical laws, not divine beings or perfect crystalline spheres. This was a profound shift in human thinking. Newton unified terrestrial and celestial mechanics with one set of mathematical laws, the same gravity, acting everywhere, following the same rules, describable with the same equations. Newton's law of universal gravitation states that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Let me break that down more carefully because this is crucial. The force between two objects depends on their masses. More massive objects exert stronger gravitational attraction. Makes sense intuitively. Earth is more massive than you, so it attracts you more strongly than you attract it. Actually, you attract Earth with exactly the same force that Earth attracts you. Newton's third law says every action has an equal and opposite reaction. When Earth pulls on you with its gravity, you pull on Earth with equal force. But Earth is so massive, roughly 6 septillion kilograms, that's a 6 followed by 24 zeros, or about 13 billion trillion pounds, that your pull on it doesn't move it appreciably. You, depending on your size, might weigh between 50 and 100 kilograms, or 100 to 200 pounds. That's the mass difference we're talking about. Earth vastly outweighs you by a factor of about 100 trillion. So the gravitational force is determined primarily by Earth's mass. When you jump, you pull Earth toward you. But Earth's acceleration is so tiny, about 1 divided by your mass ratio, that it's completely unmeasurable. Meanwhile, Earth pulls you back down with the same force. But because you're so much less massive, your acceleration is large and noticeable. You fall. Earth doesn't move appreciably, even though the forces are equal. You and a pencil across the room also pull on each other gravitationally, but so weakly you'd never notice it. The gravitational force between you and a pencil 1 meter away is real, but it's utterly negligible compared to every other force acting on you. Air currents pushing on the pencil are stronger. Electrostatic forces from nearby objects are stronger. Thermal vibrations are stronger. Exactly how weak are we talking? Let me give you some numbers that really drive this home. If you tried to build a gravitational wave detector sensitive enough to register a single person walking past the lab, the 2 arms of the interferometer would need to be roughly the distance from our Sun to Saturn, approximately 10 billion kilometers or 6 billion miles long. Anything shorter, and the gravitational signal from a person is completely swamped by quantum fluctuations and thermal noise. That's why you can feel the tiniest magnet picking up a paperclip, overcoming the gravitational pull of the entire Earth. You can feel a static shock from a doorknob, a tiny electromagnetic discharge involving a minuscule amount of charge. Yet, 2 people standing a meter apart attract each other gravitationally by less than the weight of a single bacterium. If you could somehow turn off all other forces and leave only gravity, those 2 people would eventually drift together, but it would take an absurdly long time. They'd accelerate toward each other at roughly 100 millionth of a meter per second squared. At that acceleration, it would take about 40 minutes just to move 1 centimeter closer. Gravity is 39 orders of magnitude weaker than the electromagnetic force on everyday scales. That's a trillion times weaker. Let that sink in. One of the deepest unsolved mysteries in physics is why gravity is so weak compared to the other forces. Electromagnetism, the weak nuclear force, and the strong nuclear force are all far, far stronger than gravity at comparable distances. We still don't know why. Some theories propose that gravity leaks into extra dimensions, diluting its strength in our three-dimensional space. Imagine water spreading across a table versus spreading through a sponge. The sponge has more volume to fill, so the water is less concentrated. If gravity spreads into extra dimensions that we can't see, it would be diluted, weaker in our three-dimensional experience. Others suggest that gravity's weakness is related to the Higgs field or other aspects of particle physics we don't yet understand. The hierarchy problem, as it's called, is one of the major unsolved questions in theoretical physics. But the fact remains that gravity is extraordinarily weak on human scales. The entire mass of Earth pulls on you with a force that can be overcome by the muscles in your legs jumping. And that's before we even get to the inverse square law part of Newton's equation. This is crucial for understanding how gravity works across different distances. Double the distance between two objects and the gravitational pull doesn't halve. It drops to 1/4. Triple the distance and it falls to 1/9. 10 times the distance means 1/100th the gravitational force. 100 times the distance means 1/10,000th the force. The force falls off with the square of the distance. This mathematical relationship, the inverse square law, appears throughout physics. Light intensity follows an inverse square law. Electric force follows an inverse square law. Sound intensity follows an inverse square law. There's a geometric reason for this. If you imagine a source radiating something equally in all directions, the stuff spreads over the surface of an expanding sphere. The surface area of a sphere is proportional to the square of its radius. So as the radius doubles, the surface area quadruples, and the concentration of stuff at any point on the surface is 1/4 as strong. That's the inverse square law. For gravity, this means that as you move away from a massive object, its gravitational influence diminishes rapidly. At twice the distance, 1/4 the force. At 10 times the distance, 1/100th the force. That's what makes gravity dominate only when the masses get truly enormous. On Earth, you feel gravity strongly because Earth's mass is so large and you're relatively close to its center, only about 6,400 kilometers or 4,000 miles from the center. But between you and everyday objects, gravity is negligible compared to other forces. The electromagnetic force between atoms is what keeps matter solid, what lets you touch things, what creates friction and tension, and all the structural integrity of materials. When you sit in a chair, electromagnetic forces between the atoms in your body and the atoms in the chair prevent you from passing through it. Specifically, the electrons in your atoms repel the electrons in the chair's atoms. This repulsion is electromagnetic, not gravitational. When you pick up a cup, electromagnetic forces transmit the pressure from your fingers to the cup's molecules. The molecules in your skin push on the molecules in the cup's surface, and those push on deeper molecules, and so on. All electromagnetic interactions. Gravity plays no role. Chemical bonds that hold molecules together, electromagnetic, the hardness of diamond, the strength of steel, the flexibility of rubber, all electromagnetic. Gravity only becomes important at astronomical scales, where masses are huge and electromagnetic forces tend to cancel out because matter is electrically neutral overall. A planet has equal numbers of protons and electrons, so its net electric charge is 0. Electromagnetic forces don't cause planets to attract or repel each other, but every bit of mass in the planet contributes to gravity, so gravitational forces add up. That's why gravity dominates the structure of the solar system, galaxies, and the universe. Even though it's so weak, it's the only force that matters at large scales because it's always attractive and never cancels out. Newton's equations worked beautifully for over 2 centuries. They could predict the motion of planets with incredible accuracy. Astronomers could calculate where Mars would be 10 years in the future and point their telescopes at that spot and find Mars right there. The equations explained tides, the ocean rising and falling because of the moon's gravity pulling on the water. High tide occurs when the moon is overhead, pulling water toward it, and also on the opposite side of Earth, where water is pulled less strongly than the solid Earth and so bulges away from the planet. That's why there are 2 high tides per day, roughly 12 hours apart. Newton's equations explained why planets farther from the Sun move slower in their orbits. This follows directly from Newton's laws. Mercury, closest to the Sun, zips around in just 88 days, orbiting at about 170,000 kilometers per hour, or about 105,000 miles per hour. Venus takes 225 days, orbiting at about 126,000 kilometers per hour. Earth takes 365 days, orbiting at about 107,000 kilometers per hour. Mars takes 687 days, almost 2 Earth years, orbiting at about 86,600 kilometers per hour. Jupiter takes almost 12 years, orbiting at about 47,000 kilometers per hour. Saturn takes nearly 30 years, orbiting at about 34,700 kilometers per hour. Each planet's orbital period follows precisely from Newton's laws and the inverse square law of gravity. The farther you are from the Sun, the weaker the Sun's gravitational pull, and the slower you need to move to stay in orbit. All of this was predicted by Newton's equations with stunning accuracy. Newton's laws allowed scientists to discover new planets by observing tiny irregularities in the orbits of known planets. That's how Neptune was discovered, one of the great triumphs of Newtonian physics and mathematical astronomy. The story of Neptune's discovery is worth telling because it shows how powerful Newton's laws were. In 1846, astronomers noticed that Uranus, which had been discovered in 1781 by William Herschel, wasn't moving exactly as Newton's equations predicted. Uranus had been observed for over 60 years, enough time to track its orbit carefully. By the 1840s, it was clear that Uranus was slightly off course. It was moving a little faster than predicted at some points in its orbit and slower than predicted at others. The discrepancies were small, just a few arc-seconds in position over the course of a year, but they were unmistakable to the precision instruments of the time. There were 2 possible explanations. Either Newton's laws were wrong, or there was an undiscovered planet beyond Uranus whose gravity was pulling on Uranus and perturbing its orbit. 2 mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently bet on the second explanation. They used Newton's law of gravity to work backward from the observed perturbations to determine the mass, distance, and position of a hypothetical 8th planet. This was an incredibly difficult calculation. They had to figure out where a planet would need to be to cause the specific deviations they observed in Uranus's motion. Le Verrier spent months on the calculations, solving complex equations by hand. He predicted that there should be a planet at a specific location in the sky, at a specific distance from the Sun, with a specific mass. He sent his calculations to Johann Galle at the Berlin Observatory. On September 23, 1846, Galle pointed his telescope at the predicted location. And there was Neptune, right where the math said it should be, within 1 degree of the predicted position. The planet was discovered on the first night of searching, within an hour of starting the observations. A triumph of Newtonian physics and mathematical prediction, this discovery confirmed, beyond any doubt, that Newton's laws were correct and universal. They worked not just for planets we could see, but for planets we hadn't even discovered yet. The laws were so powerful that they could predict the existence and location of an entire planet. For over 200 years, Newton's laws were considered the final word on gravity. They seemed complete, universal, capable of explaining every gravitational phenomenon in the universe. But there were small problems, tiny discrepancies that most scientists ignored because they were so small and because Newton's laws worked so well everywhere else. The most famous problem was Mercury's orbit. Mercury orbits the Sun in an ellipse, as do all planets, according to Kepler's first law, which Newton's theory explained perfectly. But that ellipse itself rotates slowly over time, a phenomenon called precession of the perihelion. The perihelion is the point in Mercury's orbit closest to the Sun. For Mercury, this point shifts slightly with each orbit, by about 0.16 arcseconds per orbit. Over centuries, the entire ellipse rotates around the Sun. This precession happens for all planets to some degree. It's caused primarily by the gravitational pull of other planets tugging on them. Venus pulls on Mercury, Earth pulls on Mercury. Jupiter, being so massive, pulls on everything in the solar system. All these gravitational influences can be calculated using Newton's laws. Newton's equations predicted how much each planet should precess based on the gravitational influence of all the other planets. For most planets, the predictions matched the observations perfectly. Earth's precession matched. Venus's precession matched. Mars's precession matched, but not Mercury's. Newton's equations predicted that Mercury's perihelion should precess by about 531 arcseconds per century based on planetary perturbations. That's roughly 0.15 degrees per century, or about 5,310 arcseconds total. The observed precession was about 574 arcseconds per century. A difference of 43 arcseconds per century remained unexplained. Now, 43 arcseconds per century might not sound like much. That's approximately 1/1800th of a degree per century. To put that in perspective, 43 arcseconds is about the angle subtended by a quarter coin viewed from 2.5 kilometers away, or about 1.5 miles, incredibly small. Over the course of a human lifetime, the error would accumulate to less than 1 arcsecond. You could observe Mercury your entire life and never notice the discrepancy. But it was real and measurable with the telescopes and timing methods available in the late 19th century. Scientists searched desperately for explanations, because this was the one crack in Newton's otherwise perfect theory. Maybe an undiscovered planet called Vulcan was orbiting closer to the Sun than Mercury, between Mercury and the Sun, pulling on Mercury and causing the extra precession. This seemed reasonable. After all, that's how Neptune had been discovered. An unexplained perturbation led to the discovery of a new planet. Astronomers looked for Vulcan eagerly. Several false sightings were reported. Some astronomers thought they had seen Vulcan transiting across the Sun's face during solar eclipses, appearing as a small dark dot against the Sun's bright surface. But these sightings were never confirmed. Different observers reported different positions. Nobody could reliably find Vulcan. It became clear that Vulcan didn't exist. The sightings were errors, sunspots misidentified as a planet, or wishful thinking. Maybe the Sun wasn't perfectly spherical. Maybe it was slightly oblate, flattened at the poles, with a larger equatorial bulge than expected. An oblate Sun would have a slightly different gravitational field than a perfectly spherical Sun. The extra mass at the equator would create additional gravitational pull that would affect Mercury differently than predicted by assuming a spherical Sun. But observations of the Sun showed it was spherical to within the measurement error. The Sun rotates slowly, about once every 25 days at the equator, and this rotation creates a tiny oblateness, but not nearly enough to explain Mercury's precession. Maybe Newton's inverse square law needed a slight adjustment. Maybe gravity didn't follow exactly an inverse square, but something like inverse 2.00001 power. A tiny deviation that would be unnoticeable for most planets, but significant for Mercury because Mercury is so close to the Sun, where gravitational forces are strongest. Some physicists proposed modifications to Newton's law, adding small correction terms, but nothing worked consistently. No adjustment to Newton's laws could explain Mercury's orbit without breaking the successful predictions for other planets. If you tweaked the equations to fix Mercury, Venus's orbit would be wrong. Fix Venus and Earth would be wrong. There was no modification that worked universally. The mystery remained unsolved for decades. It became one of the great unsolved problems of 19th century astronomy and physics. Some scientists thought the answer would be a minor correction to Newton's laws, a small adjustment that would perfect the theory. Others suspected something more fundamental was wrong, that Newton's framework was incomplete in some deep way, but nobody knew what. The mystery remained unsolved until 1915, when Albert Einstein published his general theory of relativity. Einstein's insight was radical, revolutionary, and utterly counterintuitive. Gravity isn't a force at all. Rather, it's a curvature of space-time itself. That probably sounds like meaningless word salad if you're hearing it for the first time. Curvature of space-time. What does that even mean? How can space curve? Space is just emptiness, the absence of things, the void where matter and energy exist. How can emptiness be curved? And what is space-time anyway? Isn't time separate from space? Let me explain it step by step, building up from concepts you already understand, because this is probably the most important part of this entire discussion. First, consider space and time separately, the way we normally think about them in everyday life. Space is the three-dimensional arena where things exist and move. You can move forward and backward, left and right, up and down. Those are your three dimensions of space. You can specify any location by giving three numbers, three coordinates. In a room, you might say the light bulb is 2 meters to the right, 3 meters forward, and 2.5 meters up from the corner. Three numbers, three dimensions. Time is different from space in our everyday experience. It flows in one direction from past to future, like a river flowing downhill. You experience events in a sequence, one after another. You remember the past but not the future. You can't move backward in time to visit yesterday, or jump forward arbitrarily to next year. Time seems fundamentally different from space. Space is where things happen. You can move freely through space. You can go forward, then backward, then sideways, then forward again. You have freedom of movement in space. Time is when they happen. You're stuck moving forward through time at 1 second per second. You can't stop. You can't reverse. You can't skip ahead. But Einstein showed that space and time are not separate. They're woven together into a single four-dimensional fabric called space-time, not just a mathematical trick or a convenient way of doing calculations. A description of physical reality, of how the universe actually is at its deepest level. You can't have space without time, or time without space. They're aspects of the same thing, the way length and width are aspects of a two-dimensional surface. When you move through space, you also move through time. You can't move through space without moving through time. When time passes, you're also moving through space-time, even if you're sitting still in space. Every event in the universe happens at a specific location in space-time, not just in space and time separately, but in the unified four-dimensional structure of space-time. Think about meeting a friend. You don't just specify where, the coffee shop on Main Street. You also specify when, 3 p.m. on Tuesday. The meeting happens at a specific point in space-time, defined by four coordinates, 3 for space, and 1 for time. If you change any of those coordinates, you miss the meeting. Show up at the right place, but at 2 p.m., you're early. Show up at 3 p.m., but at a different coffee shop, you're in the wrong place. Both space and time matter. They're intertwined. Here's where it gets interesting, and where Einstein's genius really shines. Space-time is not rigid like a stage or a container. It's flexible, dynamic, malleable. It can bend and curve and twist. And what causes it to curve? Mass and energy. Any object with mass or energy curves the space-time around it, warps the geometry. The more massive the object, the more it curves space-time. Earth curves space-time around it in a shallow dip. The Sun curves space-time much more because it's much more massive, about 330,000 times more massive than Earth. A neutron star curves space-time even more dramatically. A black hole curves space-time so severely that the curvature becomes effectively infinite at the center. Even you curve space-time a tiny amount with your mass. Everything with mass or energy curves space-time to some degree, though for everyday objects the curvature is unmeasurably small. Think of space-time like a stretched rubber sheet, the classic analogy that every physics popularizer uses. I'm going to use it too because despite its limitations, it works. If you place a bowling ball on the sheet, it creates a dip or depression, a curvature in the sheet. The heavier the ball, the deeper the dip. If you roll a marble near the bowling ball, the marble doesn't travel in a straight line across the sheet. It curves toward the bowling ball, following the slope of the depression created by the bowling ball's weight. From the marble's perspective, it's just following the straightest path available. But because the sheet is curved, that path curves toward the bowling ball. The marble circles the bowling ball, or spirals inward, or gets flung away, depending on its speed and direction. It looks like the bowling ball is pulling the marble, like there's a force between them, but actually, there's no pull. The marble is just following the curvature of the sheet. Similarly, Earth curves space-time around it. When you drop a ball, the ball isn't being pulled by a force. It's following the straightest possible path through curved space-time, called a geodesic. That path happens to curve toward Earth's center because of the way Earth's mass curves space-time. The analogy has limitations, and it's important to understand them. The rubber sheet is a two-dimensional surface being bent in a third dimension, downward. You can visualize the curvature because you're seeing it from outside, from a three-dimensional perspective, looking at a two-dimensional surface curving through the third dimension. But space-time is four-dimensional, and it's not bending into some higher dimension. It's intrinsically curved, meaning the curvature is a property of space-time itself, not a bending into something else. Mathematical, not visual. There's no outside perspective from which to view the curvature. We're inside space-time. The curvature is measured by how distances and times behave, not by seeing space-time curve through some extra dimension. This is hard to visualize because our brains evolved to understand three-dimensional space, not four-dimensional space-time, and certainly not intrinsic curvature. But the mathematics describes it perfectly. Einstein described this curvature with equations, the Einstein field equations, which relate the curvature of space-time to the distribution of mass and energy. These equations are complex, some of the most mathematically sophisticated equations in all of physics. They involve tensor calculus, a branch of mathematics that Einstein had to learn specifically for this purpose. He wasn't trained in tensor calculus. He had to teach himself advanced mathematics to express his ideas properly. The equations took him years to work out. He struggled, made mistakes, published wrong versions, corrected himself, and tried again. From 1907, when he had the initial insight about equivalence, to November 1915, when he finally got the equations right, was 8 years of intense intellectual labor. But the core idea is simple and beautiful. Mass and energy tell spacetime how to curve. Curved spacetime tells mass and energy how to move. It's a dynamic interplay. Matter curves spacetime. Curved spacetime affects how matter moves. That motion changes the distribution of matter, which changes the curvature, which changes the motion, and so on. A beautiful feedback loop that governs everything from falling apples to orbiting planets to expanding galaxies to the evolution of the universe itself. Objects moving through curved spacetime follow paths called geodesics. This concept is crucial to understanding how gravity works in general relativity, so let's explore it carefully. A geodesic is the generalization of a straight line to curved space. On a flat surface, the shortest path between 2 points is a straight line. You learned this in geometry class. Draw 2 points on a flat piece of paper. The shortest distance between them is a straight line. Simple, obvious. But what if the surface isn't flat? On a curved surface, like the surface of Earth, the shortest path between 2 points is a curved line. That's a geodesic. Take a globe. Pick 2 cities, say New York and Tokyo. If you stretch a string tightly between them on the globe's surface, the string will follow a great circle. A great circle is any circle that divides a sphere into 2 equal hemispheres. The equator is a great circle. Lines of longitude are great circles, but lines of latitude, except the equator, are not great circles. The Great Circle route between New York and Tokyo curves far north, passing near Alaska and the Aleutian Islands. If you look at a flat map, especially a Mercator projection, this route looks curved, even wasteful. Why not just fly straight across the Pacific from New York toward the west? But on the actual spherical Earth, the Great Circle route is shorter. It's the geodesic, the straightest possible path on a curved surface. Airplanes flying from New York to Tokyo don't fly in what looks like a straight line on a flat map. They fly along a great circle route that curves northward. That's the geodesic, the shortest path on Earth's curved surface. Pilots don't do this because of wind patterns or to avoid restricted airspace, though those factors matter too. They do it primarily because it's literally shorter. You save hundreds of miles by following the Great Circle route. You can verify this with a globe and a piece of string. Stretch the string tight between 2 cities and you'll see it follows a great circle. Any other path is longer. The same principle applies in curved spacetime, but instead of a 2-dimensional surface, we're dealing with 4-dimensional spacetime. Hard to visualize. Impossible, really. Our brains didn't evolve to visualize 4-dimensional geometry. We're stuck with 3-dimensional brains trying to understand a 4-dimensional reality. But the mathematics works the same way as for curved surfaces, just extended to more dimensions. In curved spacetime, objects follow geodesics. When you drop a ball, it's following a geodesic through the curved spacetime around Earth. When Earth orbits the Sun, it's following a geodesic through the curved spacetime around the Sun. When light from a distant star passes near the Sun and its path bends, the light is following a geodesic through the curved spacetime around the Sun. No force is needed. The objects are simply moving along the straightest possible paths through curved geometry. This is profound, a complete shift in how we think about motion and gravity. In Newtonian physics, you need forces to explain why objects don't move in straight lines. The Moon orbits Earth because Earth's gravity pulls on it. Without that force, the Moon would fly off in a straight line. Newton's first law says, an object in motion stays in motion in a straight line unless a force acts on it. So the Moon's curved path requires a force to explain it. But in general relativity, the Moon is moving in a straight line a geodesic through curved spacetime. From the moon's perspective, it's not being deflected by any force. It's moving naturally, freely, following the geometry. Earth's mass curves spacetime around it. The moon follows that curvature. No force required. The moon is in free fall, but because it's moving sideways fast enough, it keeps missing Earth. That's what an orbit is. Continuous free fall while moving sideways. Consider a thought experiment that really drives this home. Imagine you're an astronaut, floating in space far from any planets or stars, in a region where space-time is essentially flat because there's no significant mass nearby. You release a ball. The ball floats next to you, neither moving closer nor farther away. You're both following geodesics through flat space-time, and those geodesics are parallel, so you stay at constant distance. Now imagine you're standing on Earth. You release a ball, the ball falls. Why? In Newtonian physics, Earth's gravity pulls the ball down. There's a force acting on the ball. In general relativity, the ball is trying to follow its geodesic through the curved space-time around Earth. That geodesic points toward Earth's center. The ball falls because that's its natural path through curved space-time, the four-dimensional equivalent of a straight line. But wait, if the ball is following its natural path, why do you see it accelerate downward? Because you're not following your natural path. The ground is in the way, preventing you from following your geodesic. The ground exerts electromagnetic forces on your feet. The atoms in the ground repel the atoms in your feet. This electromagnetic repulsion prevents you from following your natural geodesic, which would take you toward Earth's center, just like the ball. From the ground's reference frame, from your perspective, standing still, the ball appears to accelerate downward. But from the ball's reference frame, during freefall, nothing is happening. The ball feels no force. It feels no acceleration. It's moving naturally, following its geodesic. You, standing on the ground, are the one being accelerated upward by electromagnetic forces from the ground. This perspective flip is central to understanding general relativity. What we normally call falling is actually the natural state of motion. What we normally call standing still is actually being accelerated away from your natural path. Let's think about orbital motion through this lens. The International Space Station orbits Earth at about 400 kilometers altitude. It travels at about 28,000 kilometers per hour, or about 17,500 miles per hour. At that speed and altitude, it completes one orbit every 90 minutes. The station is in freefall, continuously falling toward Earth, but because it's moving sideways so fast, it keeps missing Earth. It falls around Earth rather than into it. The station is following a geodesic through the curved spacetime around Earth. That geodesic happens to be a closed loop, an orbit. The astronauts inside feel weightless because they're also in free fall, following the same geodesic as the station. From their perspective, there's no gravity. They float around the cabin. Objects released drift in straight lines relative to them. Everything behaves as if gravity doesn't exist. But from Earth's perspective, they're constantly falling, constantly being pulled by gravity. Both perspectives are valid, describing the same physical situation from different reference frames. General relativity reconciles them by saying that free fall is the natural state. Geodesics are the natural paths through space-time. Anything that deviates from a geodesic requires a force, and by force we mean something other than gravity, like electromagnetic forces, nuclear forces, or forces from engines and rockets. Gravity itself is not a force in general relativity. It's geometry, the shape of space-time. This also explains why gravity is universal, why it affects everything the same way. Every object, regardless of its composition, mass, charge, or any other property, falls at the same rate in a vacuum. A feather and a hammer, a ball of iron and a ball of wood, an antimatter particle and a matter particle, they all follow the same geodesic if they start from the same point with the same velocity. Mass doesn't matter. Composition doesn't matter. Charge doesn't matter. None of that matters. The geodesic is determined solely by the curvature of space-time, which is determined solely by the distribution of mass and energy creating that curvature. Different objects follow the same geodesics because the geometry is the same for all of them. In Newtonian physics, this universality of freefall is a mysterious coincidence called the equivalence of inertial and gravitational mass. Inertial mass is the resistance to acceleration, how hard it is to change an object's velocity. Gravitational mass is the strength of gravitational attraction, how strongly gravity pulls on an object. These are conceptually different quantities. Inertial mass relates to Newton's second law, force equals mass times acceleration. Gravitational mass relates to Newton's law of gravity, but they turn out to be exactly equal for every object ever measured. An object with twice the inertial mass experiences twice the gravitational force, so the acceleration is the same. Force equals mass times acceleration. Double the force, double the mass, same acceleration. Newton had no explanation for why inertial and gravitational mass are equal. It's just an empirical fact, something you observe but can't derive from deeper principles within Newton's framework. It's just how nature is. But in general relativity, it's inevitable, built into the structure of the theory. There's no distinction between inertial and gravitational mass because gravity isn't a force depending on mass. All objects follow geodesics, and geodesics are determined by geometry, not by the properties of objects moving through that geometry. The equivalence of inertial and gravitational mass isn't a coincidence. It's a consequence of gravity being spacetime curvature. This is why the equivalence principle works, why you can't tell the difference between free fall in a gravitational field and floating in empty space. Because in both cases, you're following a geodesic through spacetime. In one case, the spacetime is curved by a nearby massive object. In the other case, the spacetime is flat because there's no mass nearby. But in both cases, you're moving naturally, following the geometry, experiencing no forces. Einstein realized this in 1907, what he later called the happiest thought of my life. He was sitting in his office at the patent office in Bern, Switzerland. He imagined a person falling from a roof. While falling, the person wouldn't feel their own weight. They would feel weightless, just like an astronaut in orbit. That's true, and you know it's true if you've ever experienced freefall. Jump off a diving board, and for that brief moment, you feel weightless. Ride a roller coaster over a hill, and at the top you feel momentarily weightless as the track falls away beneath you. Anyone who's been in freefall knows you feel weightless during the fall. But Einstein realized this wasn't just a feeling or a psychological trick. It was fundamental, revealing something deep about the nature of gravity. During freefall, you truly are weightless from your own perspective. There's no experiment you could do while falling that would tell you gravity exists. If you're in a closed box with no windows, falling freely, you can't tell whether you're falling in a gravitational field or floating in empty space far from any mass. Drop a pen and it falls with you at the same rate. It doesn't fall relative to you. It just floats there. Everything in your reference frame behaves as if there's no gravity. This equivalence between freefall and zero gravity is the key insight that led Einstein to general relativity. If freefall is indistinguishable from zero gravity, then standing on the ground must be equivalent to accelerating upward in a rocket. When you stand on Earth, you feel weight, because the ground is accelerating you upward through curved space-time. Sounds absurd at first. The ground isn't moving, is it? You're standing still. But remember, we're talking about four-dimensional space-time, not just three-dimensional space. In space-time, the ground is constantly accelerating you upward along the time axis, preventing you from following your natural geodesic toward Earth's center. That constant acceleration is what you feel as weight. The equivalence principle led Einstein to realize that gravity must affect not just space, but time as well. If gravity and acceleration are equivalent, and acceleration affects time as special relativity showed, then gravity must also affect time. This is one of the most profound and experimentally verified predictions of general relativity. Time itself passes at different rates depending on how deep you are in a gravitational field. Let me explain gravitational time dilation carefully, because it's one of the strangest confirmed facts about reality. In 1905, Einstein published his special theory of relativity. Special relativity showed that time is not absolute. Time passes at different rates for observers moving at different speeds. The faster you move relative to someone else, the slower time passes for you from their perspective. This is time dilation due to motion. It has been confirmed by countless experiments. Muons are subatomic particles created in the upper atmosphere when cosmic rays hit air molecules. Muons are unstable and decay in about 2 microseconds on average. That's enough time for a muon traveling at 99.9%, the speed of light, to travel about 600 meters before decaying. But muons created 30 kilometers up in the atmosphere reach sea level detectors regularly. They should have decayed long before reaching the ground. But time dilation extends their lifetime from our perspective. From the muon's perspective, time is passing normally, and it decays in 2 microseconds. But from our perspective, the muon's time is dilated because it's moving so fast, and it survives long enough to reach the ground. Atomic clocks on fast-moving airplanes run slower than identical clocks on the ground. In the Hafele-Keating experiment of 1971, physicists flew atomic clocks around the world on commercial airlines and compared them to clocks that stayed on the ground. The traveling clocks showed less elapsed time by a few hundred nanoseconds, exactly as predicted by special relativity. GPS satellites have to correct for time dilation, or their signals would be off. The satellites orbit at high speed, so their time runs slower due to motion. But they're also higher up where gravity is weaker, so their time runs faster due to gravitational time dilation. Both effects occur simultaneously, partially cancelling but not completely. Engineers have to account for both to keep GPS accurate. Now, general relativity predicts that gravity also affects time. The stronger the gravitational field, the slower time passes. Time runs slower at sea level than on a mountain. Time runs slower on Earth's surface than in orbit. Time runs slower near a massive object than far away from it. This follows directly from the equivalence principle. If gravity and acceleration are equivalent, and acceleration affects time, then gravity must also affect time. Here's how gravitational time dilation works. Imagine 2 observers, Alice on a mountain and Bob at sea level. Bob is deeper in Earth's gravitational field. Space-time is more curved where Bob is. Alice is higher up where space-time is less curved. If both observers have identical atomic clocks and they synchronize them, Bob's clock will run slower than Alice's clock. Not by much for Earth's gravity. The effect is tiny. For every second that passes on the mountain, slightly less than 1 second passes at sea level. The difference is about 1 part in 10 trillion for every meter of height difference. If you spend a year living on the ground floor of a building while your twin lives on the 10th floor, about 30 meters higher, when you meet again, you'll be about 10 nanoseconds younger, nanoseconds, billionths of a second. Completely imperceptible to human senses or to any biological process, but measurable with atomic clocks, which are accurate to better than a nanosecond. This has been tested many times with increasing precision as atomic clocks have improved. In the Pound-Rebka experiment of 1959, physicists at Harvard University sent gamma rays up a tower 22.5 meters tall. They measured a tiny shift in the frequency of the gamma rays, exactly as predicted by gravitational time dilation. Gamma rays climbing out of Earth's gravitational field lose energy, and their frequency decreases, their wavelength increases. They're gravitationally redshifted. The experiment detected a frequency shift of about 2 parts in 10 to the 15th power, incredibly tiny, but measurable and matching Einstein's predictions. In the 1971 Hafele-Keating experiment that I mentioned earlier, the effect was partially due to speed and partially due to altitude. The airplanes flew at about 10 kilometers altitude, where gravitational time dilation causes clocks to run faster than at sea level. The measured time differences included both special relativistic effects from the speed and general relativistic effects from the altitude. Both effects were observed and matched the predictions. More recently, physicists have measured gravitational time dilation over height differences of less than a meter. In 2010, researchers at NIST, the National Institute of Standards and Technology in Boulder, Colorado, used ultra-precise optical atomic clocks to measure the time dilation between two clocks separated by just 33 centimeters vertically, about 1 foot. They detected the predicted difference. One clock aged faster than the other by about 90 parts in 10 to the 18th power. This demonstrates that gravitational time dilation is not some exotic effect that only matters near black holes or neutron stars. It's happening right now, between your head and your feet. Your head is farther from Earth's center than your feet, by about 2 meters, if you're a tall person. That means your head is in a slightly weaker gravitational field. Time passes slightly faster for your head than for your feet. The difference is about 90 trillionths of a second per year for every meter of height. Over your entire lifetime, your head ages about 100 nanoseconds more than your feet if you stand upright the whole time. Completely negligible for biological processes, but real, measurable, predicted by general relativity, and confirmed by experiments. GPS satellites experience significant gravitational time dilation. They orbit at about 20,000 kilometers altitude, far above Earth's surface. At that altitude, Earth's gravitational field is weaker. Space-time is less curved. Time passes faster for the satellites than for receivers on the ground by about 45 microseconds per day due to gravitational time dilation. Meanwhile, the satellites are moving at about 14,000 kilometers per hour, or about 8,700 miles per hour. At that speed, special relativistic time dilation causes their clocks to run slower by about 7 microseconds per day. The gravitational effect is larger than the velocity effect. So the net result is that satellite clocks run about 38 microseconds per day faster than ground clocks. That might not sound like much, but light travels about 30 centimeters per nanosecond. 38 microseconds per day corresponds to about 11 kilometers of position error per day. Without correcting for relativistic effects, both special and general, GPS would accumulate errors of over 10 kilometers per day. Within a week, it would be completely useless for navigation. Engineers designed GPS to account for these effects from the very beginning. The satellite's atomic clocks are calibrated to tick at a slightly different rate than they would naturally, compensating for both relativistic effects. They're set to run slow by the right amount so that when the relativistic effects speed them up, they end up synchronized with ground clocks. When you use GPS on your phone to navigate to a restaurant or find your location, you're relying on general relativity being correct. The system wouldn't work otherwise. Every time you follow directions on your phone, you're depending on Einstein's predictions about curved spacetime and time dilation. The fact that GPS works is one of the most practical, everyday confirmations of general relativity. But gravitational time dilation has deeper implications beyond practical applications. It means time is not universal. There's no single cosmic clock ticking away the same for everyone everywhere in the universe. Time is local, dependent on your position in spacetime and your motion through it. Two events that are simultaneous for one observer might not be simultaneous for another observer at a different location or moving differently. This was already true in special relativity for observers moving at different speeds. The relativity of simultaneity means that now is not an absolute concept. What's happening right now on a distant star depends on your motion and your reference frame. General relativity extends this to observers at different depths in gravitational fields. If you're deep in a gravity well and I'm far away, what I call right now and what you call right now are different. Our nows don't align. Consider a thought experiment. Two astronauts, Alice and Bob, synchronize their watches while floating together in deep space. Alice stays in orbit around Earth. Bob descends to the surface in a spacecraft. They agree to wait 1 hour by Alice's watch, then Bob will return. When Bob returns to orbit and they compare watches, Alice's watch shows 1 hour has passed. Bob's watch shows slightly less than 1 hour has passed, maybe 59 minutes, 59 seconds, and 999 million nanoseconds. The difference is tiny, about 1 microsecond for 1 hour at Earth's surface versus in orbit, but it's real. Bob experienced less time because he was deeper in Earth's gravitational field. This isn't just Alice's perception or a trick of how signals travel. Bob literally aged less during that hour. If they repeated this experiment with precision clocks, the difference would be measurable. If they repeated it for years, Bob would age noticeably less than Alice, though still by a small amount for Earth's gravity. Near more extreme gravitational fields, the effect becomes dramatic. Near a black hole's event horizon, time dilation becomes enormous. Imagine watching someone fall toward a black hole from a safe distance. As they approach the event horizon, they appear to slow down from your perspective. Their movements become sluggish. Their clock runs slower and slower. Light from them becomes more and more redshifted as it climbs out of the deepening gravitational well. Wavelengths stretch. Colors shift toward red, then infrared, then radio waves, then longer and longer wavelengths. Eventually, they appear to freeze just outside the event horizon, never quite crossing it. Their image fades as the light becomes too redshifted to see. But from the falling person's perspective, nothing unusual happens at the event horizon. They cross it in a finite amount of their own time. Their clock keeps ticking normally from their perspective. They don't notice anything special at the moment they cross. There's no physical barrier at the event horizon, just a point of no return defined by the spacetime geometry. But outside, observers see them freeze because of extreme time dilation near the horizon. This creates an apparent paradox. From outside, the person never crosses the horizon, at least not in finite time. From their own perspective, they do cross in finite time, which is correct. Both are correct within their own reference frames. General relativity tells us that reality depends on your frame of reference, on your position and motion through space-time. There's no absolute truth about when or whether the person crosses the horizon. It depends on who's observing and from where. This might seem like philosophical wordplay, but it's fundamental to how space-time works. Different observers moving differently or positioned differently genuinely experience different realities. Not different perceptions of the same reality, but different actual sequences of events. Another consequence of gravitational time dilation is gravitational redshift, which I mentioned briefly. Light climbing out of a gravitational well loses energy. Its frequency decreases and its wavelength stretches, shifting toward the red end of the spectrum. This isn't because the light is tired from climbing or because space is expanding. It's because time passes at different rates, at different heights, in a gravitational field. Here's how it works. A photon is emitted at sea level with a certain frequency, a certain number of wave crests per second. As it climbs to higher altitude, it enters regions where time passes faster. But the photon itself doesn't change. It's still the same photon, with the same energy, in its own reference frame. However, because time is passing faster, at higher altitude, those wave crests are spread out over longer seconds from the perspective of an observer at higher altitude. The same number of crests passing per second at sea level corresponds to fewer crests per second at altitude, because the seconds are longer there. The frequency appears lower, the wavelength appears longer. The light is redshifted. Conversely, light falling into a gravitational well gains energy and is blue-shifted. This has been measured precisely many times. The Pound-Rebka experiment detected gravitational redshift over a height difference of just 22.5 meters in a tower at Harvard. The frequency shift was about 2 parts in 10 to the 15th, incredibly tiny but measurable with the technology of 1959. Astronomical observations show gravitational redshift from white dwarf stars, which are dense enough to have strong surface gravity. White dwarfs are the remnants of stars like our Sun after they've exhausted their nuclear fuel. They're about the size of Earth, but contain about as much mass as the Sun. That makes them extraordinarily dense, about 1 million times denser than water. The surface gravity is strong, hundreds of thousands of times stronger than Earth's surface gravity. Light escaping from the surface of a white dwarf is significantly redshifted. For Sirius B, a white dwarf companion to the bright star Sirius, light from the surface is gravitationally redshifted by about 80 kilometers per second equivalent. This means the light is shifted in wavelength as if the star were moving away from us at 80 kilometers per second, even though the actual motion is different. By measuring the redshift and knowing it's gravitational, rather than from motion, astronomers can determine the mass of the white dwarf. Gravitational time dilation affects everything, not just clocks and light, but all physical processes. Radioactive decay, chemical reactions, biological aging, quantum transitions, everything happens more slowly in stronger gravitational fields relative to observers in weaker fields. If you could somehow survive near a black hole's event horizon, where time dilation is extreme, you could watch the universe age rapidly. From your perspective, stars would evolve and die in what seems like fast forward from your perspective. Galaxies would merge and change. The cosmic microwave background would shift further into the infrared as the universe expands. Eventually, it would fade away as photons are stretched to undetectably long wavelengths. All while relatively little time passes for you by your own clock. This is a real effect described by the mathematics of general relativity, not science fiction. The movie Interstellar, released in 2014, depicted this with reasonable scientific accuracy. The characters visit a planet near a black hole where time dilation is severe. 1 hour on the planet equals 7 years back on their ship in orbit. The numbers are adjusted for dramatic effect, but the principle is completely sound according to general relativity. Time really does pass differently in strong gravitational fields. The consequences are profound for our understanding of reality. It means that time itself is part of the dynamic structure of spacetime, not a fixed background against which events unfold. Time is flexible, malleable, affected by mass and energy. This is radically different from our everyday intuition and from centuries of thinking about time as absolute. Before Einstein, everyone from Newton to philosophers to ordinary people thought of time as universal, a cosmic clock ticking the same for everyone everywhere. If something happens at 3 p.m., it happens at 3 p.m. for everyone in the universe simultaneously. But that's wrong. 3 p.m. for you might be 3 p.m. and 1 microsecond for someone in orbit. It might be 2:59 p.m., 59 seconds, for someone at the bottom of a deep mine shaft. It might be a completely different time for someone moving at high speed relative to you. Time is relative, local, dependent on your circumstances, on where you are and how you're moving. Two observers can genuinely experience different amounts of time between the same two events. One might age 10 years, while the other ages 1 year if they travel different paths through space-time. Both are correct within their own frames of reference. There's no absolute answer to how much time elapsed. It depends on your path through space-time. General relativity also predicts gravitational lensing, another profound consequence of space-time curvature. Light follows geodesics through curved space-time, just like everything else. Photons have no mass, but they still follow the curvature, because geodesics are determined by the geometry, not by mass. So if light passes near a massive object, its path will curve. The massive object acts like a lens, bending light that passes near it. This was one of the first predictions of general relativity to be tested observationally. It was first observed in 1919 during a total solar eclipse, an observation that made Einstein world famous. The story of that eclipse observation is worth telling because it was a dramatic moment in the history of science. Einstein published general relativity in November 1915. World War I was raging in Europe. International scientific cooperation was difficult. Communication between German scientists and British scientists was nearly impossible. But Arthur Eddington, a British astronomer, learned about Einstein's theory and recognized its importance. He also realized that one of its predictions could be tested during a total solar eclipse. Einstein predicted that the sun's gravity would bend starlight passing near it. The amount of bending was specific and different from what Newton's theory predicted. According to Newton, light shouldn't be affected by gravity at all because light has no mass. But Newton's theory could be adapted to treat light as if it had an effective mass, and that gave a prediction of bending of 0.875 arcseconds for light grazing the sun's surface. Einstein's general relativity predicted 1.75 arcseconds for light grazing the sun's surface, exactly twice the Newtonian value. The factor of 2 comes from the curvature of time as well as space. In general relativity, both space and time are curved, and both contribute to the bending of light. During a total solar eclipse, the moon blocks the sun's bright light, making it possible to photograph stars near the sun's edge. By comparing the positions of those stars during the eclipse to their known positions when the sun isn't nearby, measured at night, months earlier or later, you can detect whether their apparent positions have shifted. If Einstein was right, stars near the sun should appear displaced outward because their light has been bent by the sun's gravity. Eddington organized 2 expeditions to observe the solar eclipse of May 29, 1919. One team traveled to Sobral in northern Brazil. The other team, led by Eddington himself, traveled to Principe, an island off the coast of West Africa. Both locations were chosen because they were in the path of total eclipse and had good odds of clear weather in May. The eclipse occurred. Both teams photographed stars near the sun during totality. After careful analysis of the photographic plates, comparing star positions during the eclipse to their normal positions, both teams found that the stars appeared displaced by about 1.7 arcseconds, exactly as Einstein predicted. The results were announced in November 1919 at a joint meeting of the Royal Society and the Royal Astronomical Society in London. It was a sensation. Einstein's prediction had been confirmed. Newton's theory of gravity, which had reigned supreme for over 2 centuries, had been superseded by a new theory. General relativity had made a prediction that differed from Newton's theory, and observation favored Einstein. The next day, newspapers around the world carried the story. The Times of London's headline read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." The New York Times headline read, "Lights all askew in the heavens, men of science more or less agog." Einstein became an international celebrity overnight. Before the eclipse results, Einstein was known mainly to physicists. After the announcement, he was famous worldwide. People who had never heard of relativity suddenly wanted to know about this theory that overthrew Newton. Photographers and journalists sought interviews. Einstein received letters from admirers around the world. He became the archetypal genius, the iconic scientist whose wild hair and thoughtful expression became synonymous with intellectual brilliance. General relativity had passed its first major observational test. Today, gravitational lensing is a standard tool in observational astronomy. We see it all the time. When light from a distant galaxy passes near a massive object, like a galaxy cluster between us and that distant galaxy, the cluster's gravity bends the light. Sometimes the light takes multiple paths around the massive object, curved different amounts, and we see multiple images of the same distant galaxy. Or the galaxy gets stretched into arcs or long streaks, distorted by the lensing. Or we see Einstein rings, nearly perfect circles of light, when the alignment is just right and the distant galaxy, massive lens, and observer are almost perfectly lined up. These lensing effects are beautiful, and they're also scientifically valuable. By studying lensed images, astronomers can map the distribution of mass in the lensing object, including dark matter. Dark matter doesn't emit, absorb, or reflect light, so we can't see it directly. But it has mass, so it curves spacetime, so it lenses light from background objects. By carefully analyzing how light is bent, we can infer where dark matter is and how much of it there is. This has become one of the primary tools for studying dark matter distribution in galaxy clusters. We can see how much spacetime is curved, and from that we can infer how much mass is present, even if that mass is invisible. Galaxy clusters contain not just the galaxies you can see, but also huge amounts of dark matter forming a massive halo around the cluster. The total mass is much greater than the visible mass. Gravitational lensing reveals this dark matter by showing us its gravitational effects. Some of the most dramatic examples of gravitational lensing come from the Hubble Space Telescope. Images like the Hubble Deep Field show dozens of arcs and distorted images, all lensed background galaxies bent by foreground clusters. The MAXJ 0416.1 cluster shows spectacular Einstein arcs, long streaks of light from distant galaxies bent into nearly complete circles. The Bullet Cluster, officially designated as 1E0657-558, shows clear evidence of dark matter separated from normal matter by a collision between 2 galaxy clusters. The normal matter, visible as hot gas emitting X-rays, has been slowed by the collision, but the dark matter, which only interacts gravitationally, passed right through. Gravitational lensing shows that most of the mass is where the dark matter is, not where the gas is, providing direct evidence that dark matter exists and is separate from normal matter. Gravitational lensing can also be used to discover exoplanets through a technique called gravitational microlensing. If a star with a planet passes in front of a more distant background star, The foreground star's gravity focuses light from the background star, creating a temporary brightening. If the foreground star has a planet, the planet's gravity creates an additional spike in brightness during the event. By monitoring millions of stars and detecting these rare microlensing events, astronomers have discovered dozens of exoplanets, including planets orbiting very distant stars and free-floating planets not orbiting any star. More dramatically, gravitational lensing sometimes creates spectacular patterns. Einstein crosses are lensing configurations where we see four images of a single distant quasar arranged in a cross pattern around a foreground galaxy. The foreground galaxy's mass curves space-time so much that light from the background quasar takes four different paths around it, each arriving at Earth from a slightly different direction. We see the same quasar 4 times, arranged symmetrically around the lensing galaxy. Einstein rings are even more perfect configurations, where the alignment is exact and the distant galaxy appears as a ring of light around the foreground lens. These dramatic lensing effects are relatively rare because they require precise alignment, but they're spectacular when they occur, and they provide powerful tests of general relativity. By measuring the exact geometry of Einstein rings and crosses, astronomers can test whether space-time curvature behaves exactly as general relativity predicts. So far, every measurement has confirmed the theory. By measuring the time delays between the multiple images, how long light takes to travel each path around the lens, astronomers can determine the expansion rate of the universe with impressive accuracy. Different paths through curved space-time have different lengths, measured not just in spatial distance but in space-time interval. Light traveling these different paths arrives at different times, even though it was emitted simultaneously. By measuring these time delays precisely and knowing the geometry of the lensing system, cosmologists can calculate the Hubble constant, the rate at which the universe is expanding. This technique provides an independent measurement of cosmic expansion that doesn't rely on traditional distance ladder methods involving standard candles like Cepheid, variable stars, and Type Ia supernovae. It's helping resolve ongoing debates about whether the universe is expanding faster or slower than our models predict, the so-called Hubble tension. Different measurement methods give slightly different values for the expansion rate, and gravitational lensing provides another crucial data point. Black holes are the most extreme example of curved spacetime that we know exists. A black hole is a region where spacetime curvature becomes so severe that nothing, not even light, can escape. The boundary of no return is called the event horizon. Once you cross the event horizon, all possible paths through spacetime, all possible geodesics, lead inward toward the center. There's no way out. Not because something is pulling you inward with irresistible force, but because space-time itself is curved so extremely that all geodesics point inward. You'd be following geodesics, moving along the straightest possible paths through space-time. But those paths all curve toward the singularity at the center. Inside the event horizon, moving toward the center isn't a choice you make. It's inevitable as moving forward in time. The future points inward. Just as you can't stop yourself from moving forward in time right now, you can't stop yourself from moving inward once you've crossed the event horizon. Moving toward the singularity is built into the geometry of space-time itself inside a black hole. Black holes form when massive stars collapse at the end of their lives, though there are other formation mechanisms too. Stars shine by nuclear fusion in their cores. Hydrogen fuses into helium, releasing energy that creates pressure supporting the star against gravitational collapse. As long as the fusion continues, the star remains stable, balanced between gravity trying to compress it and pressure from fusion pushing outward. But fusion requires fuel. Eventually, the hydrogen in the core runs out. For stars like our Sun, the core contracts and heats up, until it's hot enough to fuse helium into carbon and oxygen. The star swells into a red giant. Eventually, the helium runs out too. For stars like our Sun, that's the end of fusion. The core contracts into a white dwarf, supported by electron degeneracy pressure, a quantum mechanical effect. White dwarfs are about the size of Earth, but contain about as much mass as the Sun. They're incredibly dense, about 1 million times denser than water, about 1 ton per teaspoonful. But for more massive stars, the process continues. Carbon fuses into heavier elements. Oxygen, neon, magnesium, silicon, eventually iron. Each stage happens faster than the last, because heavier elements require higher temperatures and don't release as much energy per fusion reaction. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, hundreds of years fusing carbon, a few years fusing oxygen, and only days fusing silicon into iron. Iron is the end of the line. Fusing iron doesn't release energy. It requires energy input. So when the core fills with iron, fusion stops. The core has been supported by fusion energy, but now there's no energy source. Gravity wins. The core collapses catastrophically. In less than a second, a core the size of Earth compresses to the size of a city, about 20 kilometers across. The density becomes astronomical, exceeding the density of atomic nuclei. Protons and electrons are crushed together, forming neutrons. The core becomes a neutron star, supported by neutron degeneracy pressure. The collapse releases an enormous amount of gravitational energy, about 10% of the star's rest mass energy converted to kinetic energy and neutrinos. This energy blows the outer layers of the star apart in a supernova explosion, one of the brightest events in the universe. For a few weeks, a supernova can outshine an entire galaxy. But if the core is massive enough, more than about 3 times the mass of the Sun, even neutron degeneracy pressure can't stop the collapse. Nothing can. The core continues collapsing, compressing beyond neutron star densities, beyond any densities we can really comprehend. According to general relativity, the collapse doesn't stop. The core compresses to an infinitely small point called a singularity, a point of infinite density and infinite spacetime curvature. Most physicists don't believe singularities are physically real. They think the equations are telling us they've reached their limit, that a deeper theory incorporating quantum mechanics is needed to describe what really happens. But we don't have that theory yet. Quantum gravity remains one of the biggest unsolved problems in physics. What we do know is that an event horizon forms. The spacetime curvature becomes so strong that an event horizon emerges, a boundary in spacetime beyond which all geodesics lead inward. Light emitted inside the event horizon can't escape. It's trapped, not because something is holding it back, but because all outward-directed geodesics curve back inward. There's no outward direction in space-time, inside the horizon. The size of the event horizon depends on the mass of the black hole. For a non-rotating black hole, the Schwarzschild radius, the radius of the event horizon, is about 3 kilometers for every solar mass. A black hole with the mass of our Sun would have an event horizon about 6 kilometers across. A black hole with 10 times the Sun's mass would have an event horizon about 60 kilometers across. The supermassive black hole at the center of our Milky Way, called Sagittarius A star, has a mass of about 4 million times the Sun's mass. Its event horizon is about 24 million kilometers across, or about 17 times the diameter of the Sun. That's huge in absolute terms, but tiny compared to the size of the galaxy, which is about 100,000 light-years across. Even more massive, supermassive black holes exist at the centers of most large galaxies. The black hole at the center of the galaxy Messier 87, or M87, has a mass of about 6.5 billion times the Sun's mass. Its event horizon is about 24 billion kilometers across, or about 160 times the distance from the Sun to Earth. Enormous, yet still tiny compared to the galaxy itself. We can't see inside event horizons. No light or information can escape from inside. But we can observe the effects on surrounding matter, and we've now directly imaged the shadows of black holes. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, the black hole at the center of M87. The Event Horizon Telescope isn't a single telescope, but a network of radio telescopes around the world, working together as a virtual telescope the size of Earth. By combining data from telescopes in Hawaii, Arizona, Chile, Mexico, Spain, and Antarctica, synchronized to billionths of a second, the collaboration created an image with resolution fine enough to see a black hole 55 million light-years away. The image shows a dark region, the shadow of the event horizon, surrounded by a bright ring of hot, glowing gas. The shadow appears larger than the actual event horizon, because the black hole's gravity bends light that passes near it, creating an optical effect that makes the shadow bigger. The bright ring is gas orbiting just outside the event horizon, heated to billions of degrees by friction and magnetic fields, emitting radio waves that the telescopes detected. The size and shape of the shadow match the predictions of general relativity perfectly. This is direct observational confirmation that black holes exist and that space-time near them behaves exactly as Einstein's equations predict. In 2022, the Event Horizon Telescope collaboration released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, 4 million times the mass of the Sun, 26,000 light-years away. Much closer than M87, but actually harder to image because the gas around it is more turbulent and variable. The imaging team had to track rapid changes in the brightness and structure of the accretion disk, the swirling disk of hot gas falling into the black hole. Again, the observations matched the predictions of general relativity. The shadow is exactly the size and shape expected for a black hole of that mass. These observations confirm that supermassive black holes exist at the centers of galaxies and that space-time curvature near them is accurately described by general relativity. Gas falling into black holes heats up to millions of degrees before crossing the event horizon, emitting X-rays. We've detected thousands of stellar mass black holes this way. Black holes with masses between a few and a few tens of times the Sun's mass, formed from collapsed stars. They're typically in binary systems, orbiting a normal star, pulling gas off the companion star. The gas spirals inward, forming an accretion disk, heating up, emitting X-rays. By observing the X-rays and the orbital motion of the companion star, astronomers can determine the mass of the unseen companion. If it's more than about 3 solar masses and not emitting light, it must be a black hole. There's nothing else it could be. Neutron stars can't be more massive than about 3 solar masses. White dwarfs can't exceed about 1.4 solar masses. Only black holes can have arbitrarily large masses. We've also detected black holes through gravitational waves, which brings us to another profound prediction of general relativity. Gravitational waves are ripples in space-time itself, traveling at the speed of light, stretching and squeezing space as they pass. Einstein predicted them in 1916, shortly after publishing General Relativity. If space-time can curve, it should also be able to ripple like the surface of a pond when you throw a stone in. When massive objects accelerate, especially when they orbit each other or collide, they create ripples in space-time that propagate outward at the speed of light. These are gravitational waves, changes in space-time curvature propagating through space. Einstein thought they'd be far too weak to ever detect. He was almost right. Gravitational waves are incredibly weak, even from the most violent events in the universe. They stretch and squeeze space, but only by tiny amounts. Even waves from colliding black holes, billions of light-years away, stretch space by less than the width of a proton over a distance of several kilometers. That's about 1 part in 10 to the 21st power. Detecting them requires extraordinarily sensitive instruments capable of measuring distances to a precision better than the width of an atomic nucleus. LIGO, the Laser Interferometer Gravitational Wave Observatory, was built for this purpose. It consists of 2 facilities, one in Hanford, Washington, one in Livingston, Louisiana, separated by about 3,000 kilometers. Each facility has 2 arms at right angles, each arm 4 kilometers long, about 2.5 miles. Laser beams travel down the arms, bouncing between mirrors at the ends. If a gravitational wave passes through, it stretches one arm and squeezes the other by a tiny amount. The laser beam in the stretched arm takes slightly longer to travel back and forth. The laser beam in the squeezed arm takes slightly less time. By measuring the interference pattern when the laser beams recombine, LIGO can detect these tiny differences in arm length. The sensitivity is astonishing. LIGO can measure length changes smaller than 1/1000th the width of a proton. That's 100 million times smaller than a hydrogen atom. To put this in perspective, if the distance from Earth to the nearest star, Proxima Centauri, about 4 light-years, were one of LIGO's arms, LIGO could detect a length change smaller than the width of a human hair. The level of precision is almost unbelievable. The mirrors must be isolated from every possible source of vibration. Earthquakes, ocean waves, traffic, even the thermal motion of atoms in the mirrors create noise that threatens to swamp the signal. The mirrors are suspended by elaborate systems of pendulums to isolate them from ground vibrations. The vacuum tubes are kept at ultra-high vacuum to prevent air molecules from disturbing the laser beams. The laser frequencies are stabilized to parts per trillion. Every imaginable source of noise must be controlled or accounted for. On September 14, 2015, LIGO detected its first gravitational wave. The signal came from 2 black holes, each about 30 times the mass of the Sun, orbiting each other and spiraling inward, 1.3 billion light-years away. As they orbited, they emitted gravitational waves, losing energy, and their orbital radius decreased. The orbital period got shorter and shorter. The black holes spiraled faster and faster in an accelerating death spiral. The gravitational wave frequency increased, sweeping upward over a fraction of a second. LIGO heard this as a chirp, a rapidly rising tone like a bird's call, but at frequencies below human hearing, more like a deep vibration. Finally, the black holes merged. 2 black holes became one. In a fraction of a second, about 3 times the mass of the Sun was converted directly into gravitational wave energy. That's more power than all the stars in the observable universe combined emit as light during that same fraction of a second. But the energy was emitted as gravitational waves, not light, so you couldn't see it with a telescope. The gravitational waves traveled through space for 1.3 billion years, expanding across the universe. When they reached Earth, they stretched and squeezed LIGO's arms by about 1/1000th the width of a proton, but LIGO detected it. Both detectors, Washington and Louisiana, saw the same signal, arriving at Louisiana 7 milliseconds before Washington because gravitational waves travel at the speed of light and Louisiana is slightly closer to the source. Direction: the signal matched the predictions of general relativity perfectly. The waveform, the way the frequency and amplitude changed over time, matched computer simulations of black hole mergers calculated using Einstein's equations. From the waveform, scientists could determine the masses of the black holes, about 36 and 29 solar masses, their spin rates, their distance, about 1.3 billion light-years, and the mass of the final merged black hole, about 62 solar masses. Notice that 36 plus 29 equals 65, but the final black hole is only 62 solar masses. 3 solar masses were converted to gravitational wave energy according to Einstein's famous equation E equals mc squared. 3 times the mass of the Sun, turned into pure energy, emitted as gravitational waves in a fraction of a second. This was a monumental achievement in the history of science and technology. Direct detection of gravitational waves, a phenomenon predicted 100 years earlier, confirmation that black holes exist and merge exactly as general relativity describes. Confirmation that space-time can ripple and that those ripples travel at the speed of light, and opening an entirely new way to observe the universe, a new window on cosmic events. The discovery was announced in February 2016, and the leaders of the LIGO collaboration were awarded the Nobel Prize in Physics in 2017. Since that first detection, LIGO and its partner Virgo in Italy, and more recently CAGRA in Japan, have detected dozens of gravitational wave events. Most are from merging black holes with masses ranging from a few solar masses to almost 100 solar masses. Some are from merging neutron stars, the ultra-dense remnants of massive stars that didn't quite have enough mass to form black holes. One detection in particular stands out. On August 17, 2017, LIGO and Virgo detected gravitational waves from 2 neutron stars colliding. This event, designated GW170817, was special because it was also observed by telescopes in gamma rays, X-rays, optical light, infrared, and radio waves. The first multi-messenger observation of a cosmic event, combining gravitational waves with electromagnetic observations. Within seconds of the gravitational wave detection, gamma-ray satellites detected a short gamma-ray burst from the same direction. Telescopes around the world swung toward the source. Over the following hours and days, they watched as the collision site brightened in optical and infrared light, creating a kilonova, an explosion brighter than a nova, but not as bright as a supernova. The kilonova spectroscopy showed signatures of heavy elements being created in the explosion. When neutron stars merge, the extreme temperatures and densities create conditions where rapid neutron capture can occur, building up heavy elements like gold, platinum, uranium. This observation confirmed that neutron star mergers are one of the primary sources of heavy elements in the universe. All the gold and platinum on Earth, in your jewelry or electronics, likely came from neutron star mergers billions of years ago, before our solar system formed. We're made of star stuff, as Carl Sagan said, but some of that star stuff came from the most violent events in the cosmos, collisions so powerful they shake the fabric of space-time itself. The multi-messenger observation of GW170817 demonstrated the power of combining gravitational wave astronomy with traditional electromagnetic astronomy. Gravitational waves tell us about the masses and motions of the merging objects. Electromagnetic observations tell us about the matter ejected, the elements created, the energies involved. Together, they give us a complete picture of what happens during these cataclysmic events. Gravitational wave astronomy is still in its infancy, but it's already transforming our understanding of the universe. Before LIGO, we knew black holes existed, but we had only indirect evidence. Now we've detected dozens of black hole mergers, confirming that stellar mass black holes are common and that they do merge when they're in binary systems. We've measured black hole masses more accurately than ever before. We've determined that black holes can have a wide range of masses, from a few solar masses up to about 100 solar masses for stellar mass black holes. We've found that some black holes are spinning rapidly, nearly as fast as general relativity allows. We've learned about neutron star mergers and their role in creating heavy elements. We've tested general relativity in extreme conditions, strong gravitational fields, high speeds, massive objects, and it passes every test. The gravitational waveforms match the predictions precisely. Future gravitational wave detectors will be even more sensitive. LIGO is being upgraded. Virgo is being upgraded. CAGRA is operational and improving. LIGO India is being built. These detectors will work together as a global network, pinpointing sources more accurately and detecting weaker signals. There are plans for space-based gravitational wave detectors. LISA, the Laser Interferometer Space Antenna, will have arms millions of kilometers long, allowing it to detect lower-frequency gravitational waves that LIGO can't see. Lower-frequency waves come from more massive black holes, supermassive black holes merging in galactic centers, events that happen over hours or days rather than fractions of a second. LISA will observe supermassive black hole mergers throughout the universe, probing the formation and evolution of galaxies. It will also detect gravitational waves from other sources like binary white dwarfs and maybe even primordial gravitational waves from the early universe. There's also the tantalizing possibility of detecting primordial gravitational waves, ripples in spacetime produced in the first moments after the Big Bang. These waves would carry information about the universe when it was far younger and smaller than anything we can currently observe with electromagnetic telescopes. Detecting them would be a monumental achievement, opening a window into the earliest moments of cosmic history. Current experiments search for these primordial waves by looking at the cosmic microwave background, the afterglow of the Big Bang. Gravitational waves passing through space in the early universe would have left a distinctive pattern in the polarization of this ancient light. A swirling pattern called B modes that would be the smoking gun signature of inflation, the hypothesized period of exponential expansion that occurred in the first fraction of a second after the Big Bang. The stakes are enormous. Detecting primordial gravitational waves would confirm inflation occurred, tell us about the energy scale at which it happened, and potentially reveal physics operating at energies 1 trillion times higher than anything we can achieve in particle accelerators. It would be like having a telescope that sees back to when the universe was only a tiny fraction of a second old, revealing conditions closer to the Big Bang than any other observation method can access. Beyond pure science, understanding gravity has practical technological implications. GPS is the most obvious example, but there are others. Precision timekeeping relies on understanding relativistic effects. Atomic clocks are now accurate enough that moving them between floors of a building creates measurable time differences. These clocks are used for synchronizing communications networks, financial transactions, scientific experiments, and much more. Gravity assists in spacecraft navigation. Use the curvature of space-time around planets to change spacecraft trajectories without using fuel. Voyager 1 and Voyager 2 used gravity assists from Jupiter and Saturn to reach the outer solar system. The Parker Solar Probe uses repeated gravity assists from Venus to gradually lower its orbit closer to the Sun. These maneuvers work because of how geodesics behave in curved space-time. Understanding general relativity allows mission planners to calculate precise trajectories that would be impossible without Einstein's theory. Let me give you a sense of how general relativity has been tested. It's one of the most precisely confirmed theories in all of science. Every prediction it has made has been confirmed, often to extraordinary precision. Gravitational time dilation has been measured with atomic clocks on airplanes, satellites, and even separated by less than a meter of height, confirmed to parts per trillion or better. GPS relies on it every day, correcting for relativistic effects billions of times per second. Gravitational lensing has been observed countless times. We see lensed images of distant galaxies regularly. Einstein rings and arcs are common features in deep space images from Hubble and other telescopes. The amount of bending matches general relativity's predictions precisely. The perihelion precession of Mercury, the problem that puzzled astronomers for decades, was explained perfectly by general relativity. The 43 arcseconds per century that Newton couldn't account for falls right out of Einstein's equations. No undiscovered planet needed, no modifications to the inverse square law, just spacetime curvature near the Sun. Gravitational waves have been detected, and their waveforms match the predictions exactly. The frequency evolution, the amplitude, the ring down after the merger, all match what general relativity says should happen when black holes or neutron stars merge. Frame dragging, where a rotating massive object drags spacetime around with it, has been measured by satellites like Gravity Probe B. This is a subtle effect predicted by general relativity. A gyroscope in orbit around a rotating object like Earth will gradually change its orientation because spacetime itself is being twisted by Earth's rotation. Gravity Probe B measured this effect and confirmed it to within 1% of the predicted value. The expansion of the universe is described by general relativity applied to cosmology. The Friedmann equations, derived from Einstein's field equations, describe how the universe evolves. The cosmic microwave background, the afterglow of the Big Bang, matches the predictions of general relativity combined with particle physics. The temperature fluctuations, the power spectrum, the polarization patterns, all match the predictions to remarkable precision. Black hole shadows have been imaged by the Event Horizon Telescope and match the predictions. The size, shape, and behavior of the shadows around M87 and Sagittarius A star are exactly what general relativity says they should be for black holes of those masses. Every single test has confirmed the theory, often to astonishing precision. We're talking about measurements accurate to 1 part in a trillion, or better in some cases. And general relativity passes every test. Consider the Shapiro delay, another subtle prediction. When light or radio waves pass near a massive object, they don't just have their path bent, they're also delayed. The waves take longer to travel because they're passing through more severely curved spacetime, where the geometry effectively increases the distance traveled. This was predicted by Erwin Shapiro in 1964 and first measured using radar signals bounced off Venus and Mercury. When Venus or Mercury passes behind the Sun from Earth's perspective, radio signals traveling to and from the planets are delayed by up to 200 microseconds compared to when the planets are not near the Sun. This delay matches general relativity's predictions precisely and has been measured repeatedly with increasing accuracy using spacecraft like Cassini orbiting Saturn. General relativity has been tested over a huge range of conditions. Weak fields like Earth's gravity, tested with GPS and atomic clocks. Strong fields like neutron stars and black holes, tested with gravitational waves and X-ray observations. High speeds approaching the speed of light, tested with particle accelerators and cosmic ray observations. Cosmological scales, tested with observations of the cosmic microwave background and large-scale structure of the universe. In every regime, every test, every observation, general relativity is confirmed. But general relativity is not complete, and this is important to understand. We know it breaks down in certain situations where quantum mechanics becomes important. At the center of a black hole, the equations predict a singularity, a point of infinite density and infinite curvature. Most physicists don't believe singularities are physically real. They think the equations are telling us they've reached their limit, that a deeper theory incorporating quantum mechanics is needed. Similarly, at the moment of the Big Bang, general relativity predicts a singularity where the entire universe emerged from a point of infinite density. Again, This probably means the theory breaks down under those extreme conditions. The problem is that general relativity is a classical theory. It doesn't include quantum mechanics, our other fundamental theory of nature. Quantum mechanics describes the microscopic world of atoms, particles, quantum fields. It's based on probabilities, uncertainty, discrete energy levels, wave-particle duality. General relativity describes the macroscopic world of stars, galaxies, spacetime itself. It's based on smooth, continuous geometry, deterministic evolution, classical fields. Both theories work brilliantly in their respective domains, tested to extraordinary precision, but they're incompatible in a deep way. When you try to apply both to the same situation, like the interior of a black hole or the first instant of the Big Bang, they give contradictory answers. General relativity says space-time is smooth and continuous at all scales. Quantum mechanics says everything is discrete and probabilistic at small scales. General relativity treats space-time as a fixed background on which quantum fields exist. But quantum mechanics, when pushed to its logical conclusions, suggests that space-time itself must be quantized, that there should be quantum fluctuations in the geometry of space-time. These contradictions point to the need for a unified theory of quantum gravity, a theory that reconciles general relativity and quantum mechanics, that describes how space-time behaves at the smallest scales where quantum effects become important. String theory is one candidate for quantum gravity. It proposes that particles are actually tiny vibrating strings, about the Planck length in size, roughly 10 to the minus 35 meters. Different vibrations correspond to different particles: electrons, quarks, photons, even gravitons. The hypothetical quantum particles of gravity all emerge as different vibration patterns of the same fundamental strings. In string theory, gravity emerges naturally from the vibrations of strings, and space-time at the smallest scales has additional dimensions, perhaps 6 or 7 extra dimensions curled up so small we can't detect them. Loop quantum gravity is another candidate. It proposes that space-time itself is made of discrete quantum loops, that space is not infinitely divisible but has a granular structure at the Planck scale. Area and volume are quantized, coming in discrete units. In this picture, the smooth space-time of general relativity is an approximation that emerges at large scales from the underlying quantum structure. Both theories are highly mathematical, and neither has been experimentally confirmed yet. We don't have the technology to probe the Planck scale, where quantum gravity effects become important. That would require energies far beyond what any particle accelerator can achieve, energies comparable to the Big Bang itself. But we're making progress theoretically, developing the mathematics, exploring the consequences, looking for ways these theories might be tested indirectly. Maybe we'll find signatures in the cosmic microwave background, or in the behavior of black holes, or in gravitational waves from the early universe. Someday, we might have a complete theory of quantum gravity that unifies general relativity and quantum mechanics. Until then, we're using general relativity for large-scale phenomena where quantum effects don't matter, and quantum mechanics for small-scale phenomena where gravitational effects don't matter. Both theories are incredibly successful in their domains, but we know there's a deeper theory waiting to be discovered. What does all this mean for our understanding of the universe? It means that reality is far stranger and more beautiful than our everyday experience suggests. Space and time are not the rigid, unchanging stage on which events play out. They're dynamic, flexible, woven together into space-time, curved by mass and energy. Gravity is not a force pulling objects together across empty space. It's the geometry of space-time, the shape of the four-dimensional fabric of reality. Objects move along geodesics, following the curvature, experiencing no force when they're in free fall. When you're standing on Earth, you're not being pulled down by gravity. You're being accelerated upward by the electromagnetic forces from the ground, prevented from following your natural geodesic through curved spacetime. When you're falling, you're not being pulled. You're finally free to move naturally through spacetime, following its geometry. Time is not universal, not the same for everyone everywhere. It passes at different rates, depending on how fast you're moving and how deep you are in a gravitational field. Your head ages slightly faster than your feet because it's farther from Earth's center where spacetime is less curved. GPS satellites age faster than ground clocks because they're higher up where spacetime is less curved, even though they're moving fast, which makes them age slower. The net effect is carefully calculated and compensated for. The universe is expanding, not galaxies moving through space, but space itself stretching, carrying galaxies apart. And that expansion is accelerating due to dark energy, a mysterious component that makes up about 68% of the universe's total energy. Black holes exist, regions of space-time so curved that not even light can escape. We've seen their shadows, detected their mergers through gravitational waves, measured their masses and spins. Gravitational waves are real, ripples in space-time traveling at the speed of light, carrying information about the most violent events in the universe. We've detected dozens of them, opened an entirely new window on the cosmos. All of this follows from Einstein's insight that gravity is space-time curvature, not a force, but geometry. The implications are profound, philosophical, practical, technological. Consider the practical applications I mentioned. GPS navigation depends on general relativity. Without Einstein's equations, your phone couldn't tell you where you are or how to get somewhere. Precision timekeeping relies on understanding relativistic effects. The most accurate clocks in the world measure the passage of time to 18 decimal places, accurate enough to detect time dilation from moving them a few centimeters. These clocks synchronize global communications, financial transactions, scientific experiments. Gravitational lensing is used as a tool to study the universe. We can magnify distant objects, see galaxies that would otherwise be too faint to observe. We can map the distribution of dark matter by observing how it lenses background galaxies. We can detect exoplanets through gravitational microlensing. Gravitational wave astronomy is revealing events we could never see with light. Black hole mergers, neutron-star collisions, maybe eventually the Big Bang itself. Spacecraft navigation uses gravity assists, carefully calculated trajectories through curved spacetime that save fuel and enable missions that would otherwise be impossible. The philosophical implications are equally profound. General relativity has taught us that our intuitions about space and time can be profoundly wrong. We evolved to navigate a world of moderate speeds and weak gravity. Our brains are wired to think space is flat and time is universal because that's a good approximation for everyday life. But when you probe deeper, when you approach the speed of light or enter strong gravitational fields, those intuitions break down. Reality is not what it seems. Space and time are not fundamental in the way we think. Some physicists think space-time itself might be emergent, that at the deepest level, reality is described by something else entirely, and space-time emerges from that more fundamental description, the way temperature emerges from the motion of atoms. Temperature isn't a fundamental property. It's a statistical property of many particles moving. Maybe space-time is similar. Maybe at the quantum level there's no space or time, just relationships between quantum states, and space-time emerges when you zoom out and look at large scales. These are speculative ideas, but they're taken seriously by theoretical physicists because general relativity has taught us that space and time are not what we thought they were. If Einstein could overthrow Newton's view of absolute space and time, maybe our understanding of space-time will be overthrown by an even deeper theory. What will we discover next? The future of gravitational research is exciting. More sensitive gravitational wave detectors are being built. LIGO is being upgraded to higher sensitivity. Virgo is being upgraded. KAGRA in Japan is operational. LIGO India is being constructed. These detectors will work together as a global network, pinpointing sources more accurately, detecting weaker signals, observing more distant events. LISA, the Space-Based Gravitational Wave Observatory, is planned for launch in the 2030s. With arms millions of kilometers long, it will detect supermassive black hole mergers, observe the gravitational wave background from millions of binary white dwarfs, maybe detect primordial gravitational waves from the Big Bang. The Event Horizon Telescope is being expanded, more radio telescopes joining the network, higher resolution images of black hole shadows. Maybe we'll image the photon ring around a black hole, a bright ring caused by light orbiting multiple times before escaping. Maybe we'll observe black hole jets in unprecedented detail, plasma streaming out from near the event horizon at nearly the speed of light. New tests of general relativity are being designed, experiments with atomic clocks in space to measure gravitational time dilation with even greater precision, tests of the equivalence principle to see if it holds for antimatter. Maybe we'll find a crack, a tiny deviation from general relativity that points the way to quantum gravity. Or maybe general relativity will keep passing every test, and we'll need a different approach, theoretical insights, mathematical breakthroughs. Here's something to keep in mind as we wrap up. General relativity is over a century old. Einstein published it in 1915. For decades, it was mostly a theoretical curiosity, tested in a few specific situations, but not widely applicable to practical problems. Newton's laws were good enough for most purposes. But as technology advanced, general relativity became essential. GPS wouldn't work without it. Gravitational wave detectors need it to interpret their signals. Black hole imaging relies on its predictions. Precision timekeeping requires it. We're now living in an era where general relativity is not just a theoretical framework, but a practical tool. And it's opening new frontiers, new ways to observe and understand the universe. Gravitational wave astronomy is in its infancy. We've detected dozens of events, but that's just the beginning. As detectors improve, we'll detect thousands, build up statistical samples, study populations of black holes and neutron stars, probe the formation and evolution of compact objects. We might detect gravitational waves from cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe. We might detect waves from phase transitions in the early universe when fundamental forces separated. We might detect the gravitational wave background from the Big Bang, opening a window on the first moments of cosmic history. Every new window on the universe has revealed surprises. When we first observed the sky in radio waves, we discovered pulsars, rapidly rotating neutron stars beaming radio waves like cosmic lighthouses. We discovered quasars, supermassive black holes in distant galaxies, accreting matter and outshining entire galaxies. We discovered the cosmic microwave background, the afterglow of the Big Bang. When we first observed in X-rays, we discovered X-ray binaries, neutron stars and black holes, accreting matter from companion stars. We discovered supernova remnants, the expanding shells of debris from exploded stars. We discovered hot gas in galaxy clusters, revealing the large-scale structure of the universe. When we first observed in gamma rays, we discovered gamma-ray bursts, the most powerful explosions in the universe, aside from the Big Bang itself. Gravitational waves will surely reveal phenomena we haven't imagined yet. Black holes and neutron stars we can't see any other way. Events in the early universe we can't probe with light. Maybe entirely new types of objects or phenomena that only reveal themselves through their gravitational wave signatures. What should you take away from tonight? First, gravity isn't a force in the way you've been taught. It's the curvature of space-time. Objects follow geodesics through curved space-time. When you feel weight, you're feeling electromagnetic forces preventing you from following your natural geodesic. In freefall, you're weightless because you're finally free to move along that natural path through space-time. Second, space and time are not separate entities but aspects of a unified four-dimensional fabric called space-time. Space-time is dynamic, curving in response to mass and energy. This curvature affects how objects move, which in turn affects the curvature, a beautiful interplay that gives rise to all gravitational phenomena. Third, general relativity has been confirmed by countless experiments and observations to extraordinary precision. From the precession of Mercury to the detection of gravitational waves to images of black hole shadows, every test has supported Einstein's theory. The GPS in your phone corrects for relativistic effects billions of times per second. Gravitational lensing reveals dark matter distributions. Gravitational wave detections opened an entirely new window on the universe. Fourth, we're living in a golden age of testing and applying general relativity. Technology has advanced to the point where we can measure effects that were once purely theoretical. We're detecting gravitational waves from colliding black holes. We're imaging black hole shadows. We're measuring time dilation over height differences of centimeters. And Einstein's century-old theory continues to describe reality perfectly. Fifth, there are still mysteries and open questions. Dark matter makes up 27% of the universe, and we don't know what it is. Dark energy makes up 68%, even more mysterious. Quantum gravity remains undiscovered. The theory that will unify general relativity and quantum mechanics, the interior of black holes, the first instant of the Big Bang, the ultimate fate of the universe, all open questions. General relativity gives us the framework, but it doesn't have all the answers. We need new physics, new theories, new insights. And sixth, reality is stranger than it appears. Your everyday experience of gravity as a downward pull is incomplete. What you're actually experiencing is the curvature of space-time and the resistance of matter to moving along geodesics. When you look up at the moon, you're seeing an object in freefall, endlessly circling Earth, because that's the geodesic it follows through curved space-time. When you drop a ball, you're watching it follow its natural path through the geometry of space-time. The universe operates according to these principles, whether you understand them or not. But understanding them gives you a deeper appreciation for the reality you inhabit. You're not standing on solid ground with a force pulling you down. You're accelerating upward through curved space-time, held by electromagnetic forces from the ground that prevent you from following your geodesic. That's what weight is. That's what you're feeling right now. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. We're tiny creatures on a small planet orbiting an ordinary star in an unremarkable galaxy. Yet we've figured out the fundamental laws governing cosmic scale phenomena. We've measured the curvature of space-time. We've detected ripples in space-time from black holes colliding a billion light-years away. We've imaged the shadows of supermassive black holes at the centers of galaxies. We've traced the history of the universe back to fractions of a second after the Big Bang. This is extraordinary. It suggests that the universe is fundamentally knowable, that the laws of physics are the same everywhere, that we can figure them out through careful observation, experimentation, and reasoning. That should give you hope. We're not helpless in the face of cosmic mysteries. We can understand. We have understood. and we'll continue to understand more. Science is a process of continual refinement. Each generation builds on the work of the last, getting closer to a true understanding of reality. Newton gave us a framework that worked brilliantly for over 2 centuries. Einstein gave us a deeper framework that encompasses Newton's as a special case and extends our understanding to realms Newton never imagined. Someday, perhaps soon, someone will give us an even deeper framework that encompasses Einstein's theory and reveals new aspects of reality. Quantum gravity, perhaps, or something even more fundamental. The journey continues. So the next time you think about gravity, don't think of it as a mysterious force pulling things down. Think of it as the shape of space-time, the geometry of the 4-dimensional fabric of reality. Think of yourself as moving through curved space-time, following its contours, experiencing its curvature. You're not standing still on a flat Earth with gravity pulling you down. You're accelerating upward through curved space-time, held in place by the electromagnetic forces from the ground. The ground is pushing you up constantly, preventing you from following your natural geodesic, which would take you toward Earth's center. That's weight. That's what you feel right now. And out there in space, planets are following their geodesics around stars. Stars are following their geodesics around galactic centers. Galaxies are following geodesics through the larger scale curvature of cosmic space-time. Light from distant galaxies has been traveling for billions of years through expanding space-time, carrying information about the ancient universe. Gravitational waves from cataclysmic events ripple through space-time at the speed of light, stretching and squeezing space as they pass, bringing us news of cosmic collisions. Black holes sit in regions where space-time curvature becomes so extreme that not even light can escape, where all geodesics point inward to the singularity. All of this is described by Einstein's equations, mathematical expressions that relate the curvature of space-time to the distribution of mass and energy. All of it follows from the idea that gravity is geometry. It's been over a century since Einstein published general relativity. In that time, it's been tested in countless ways, in laboratories and particle accelerators, with atomic clocks and GPS satellites, by observing planets and stars and galaxies and black holes. It's made predictions that seemed absurd, but turned out to be true. Black holes were considered science fiction for decades, mathematical curiosities that couldn't possibly exist in reality. Now we've imaged them, seen their shadows, detected their mergers. Gravitational waves were thought to be undetectable, too weak to ever measure. Now we observe them regularly, opening an entirely new window on the universe. Gravitational lensing was a curious prediction with no practical application. Now it's a standard astronomical tool for studying dark matter and distant galaxies. Time dilation was a theoretical oddity. Now it's essential for GPS navigation and precision timekeeping. The theory has survived every challenge, passed every test, made predictions that were confirmed decades later when technology caught up. And it's given us a picture of the universe that's richer, stranger, and more beautiful than anyone imagined before Einstein. A universe where space and time are flexible, where black holes and gravitational waves and cosmic expansion are natural consequences of geometry, where gravity isn't a force, but the shape of reality itself. Thanks for staying with me through this deep dive into the nature of gravity and space-time. If you found this journey through Einstein's universe compelling, a like or subscribe would help more people discover these ideas. The universe is vast and complex, full of mysteries and wonders, but it's also comprehensible. We can figure it out. We are figuring it out. One observation, one experiment, one theoretical insight at a time. Keep looking up, keep questioning, keep seeking to understand. Because in the end, that's what makes us human. The drive to comprehend the cosmos, to see beyond appearances, to grasp the deeper truths. Gravity isn't pulling you down. You're accelerating upward through curved space-time, and that makes all the difference.